Hello YouTube, welcome back. I've had zero time to get into the shop to work on the guns, so I've decided, since several people have asked me how to do this, to explain how the cutters that I've been making and how it's done. I'm absolutely no expert on making cutters, but I do know what works for me, and I'm absolutely willing to pass that on to anybody else. Since you can cut in either direction, horizontally or vertically, there's of course going to be a different cutter setup for each of them, and I'm going to explain the horizontal first. A slitting saw would be a good example for this. Every cutter has several things in common. They will all have a rake angle, and they will all have some sort of a relief angle. I'm not going to explain all the intricacies of tool geometry. There are hundreds and hundreds of videos out there explaining it, but I will give some rules of thumb. Several things happen when you cut into a piece of material, and what happens determines the rake and the relief, along with the type of material you're cutting. The first and foremost thing you got to worry about is heat. I know this is pretty basic to some of you out there, but I'm going to explain it for the people that may not know quite as much about it and could benefit from it. All tool steels are hardened by heating them up and quenching them in either water or oil. This sudden temperature change or shock makes the tool steel hard. When you reheat steel, it will re-soften. And for the purpose of this video, that's all the more I'm going to go into it. Okay, so why does heat affect the geometry of the tool? One reason is the tool's mass. The steel in the cutter acts as a heat sink. This pulls away heat from the cutting edge. In O1 tool steel, which is usually what I use to make a cutter, it starts to become soft again at around 500 or 600 degrees, about the time it starts to turn blue. I've had some people ask me why I run cutters so slow. Well, this is the exact reason. When you run it slower, it slows down the amount of friction that you get, and it gives time for the mass of the tool to pull the heat away from it. There's some good videos on YouTube that I tried to find again, but I couldn't, that shows a magnified view of the cutter. The very tip will actually glow red. Well, that glowing red means it's up above 500 or 600 degrees, and that little tip area will get red, soft, and wear off. This is the entire reason that cutting fluid and coolant will help prolong the life of the tool, is it simply pulls heat away from it and reduces friction. This is far more important in O1 tool steel or any high carbon steel that you would use to make a cutter out of. High speed steel has a much higher working hardness than carbon steel. And all this means is that it takes a much higher temperature to soften the steel. Because of this, you can run the machine at a much higher speed, hence the term high-speed steel. So why don't I use high-speed steel for my cutters, you might ask? Because there's a special heat treating process for high-speed steel that gives it that high working hardness. If you heat treat high-speed steel in the same manner that you do the high-carbon steel, it will actually act just like high-carbon steel. It will lose its hardness at a relatively low temperature. So in order for me to make a cutter out of it, I would either have to work on it while it's already hard or try to reproduce the heat treatment process. So it's just easier just to get the O1 tool steel, heat treat it the way I always do, and run it the way I always have. Okay, so now we'll talk about another reason for tool geometry, and that's just flat out strength. If you make a steeper angle on the cutting edge, you take away a lot more material, which just flat out makes it weaker because there isn't as much steel there. This is why you will see a less steep angle for steel than you would for aluminum or wood. The material is much harder to machine off, so it needs something much stronger to keep from crumbling the edge off of the tool. The sharper the angle of the rake, the easier the chips evacuate off of the material. This can also reduce temperature. Over the years, manufacturers have figured out what the happy medium is between the sharp angle and the strength. And for steel, that's usually in between 10 and 15 degrees, depending on the alloy of the steel and how hard it is. Okay, now with all the basics out of the way, how do you actually make the cutter? Here we can imagine a piece of round bar stock and a 4-jaw chuck. I'm going to remove the 4-jaw chuck in the illustration just to simplify things. I mostly just showed it to give you the orientation of the bar stock. Okay, so let's imagine I take an end mill and I cut it to the center line of this bar stock, trying to make my cutter surface. What is it that I'll end up with? I would end up with a cutting surface with zero rake at all, or a neutral cutting angle. This doesn't help me very much, because for most materials and most applications, you need a positive rake. So how do I go about getting this positive rake? One way would be to tilt the head of the mill to the desired angle and cut the rake. The problem with this is then you have to go through all the process of retramming the head in to make it square with the table again. The method that I use the most is to cut past dead center. So you might ask, how does cutting past dead center make a rake angle? That doesn't make any sense. It's still cutting 90 degrees to the table. Well, the reason is when that part rotates around and the cutting edge is at the center line, you now have your positive rake. A good exaggerated example would be a router bit. This one has been cut way past dead center, which makes a very steep rake angle which will go through soft material quickly. Notice how the cutting edges are actually parallel to each other. Okay, so here's some rule of thumb. The more you go past dead center, the higher the rake angle increases. So if you're making a cutter for steel or some other hard material, you want to stay closer to dead center, and if you're making a cutter for something soft, the further past dead center you want to go. Okay, I'm going to talk a little bit about the relief angle of a cutter like this. I had somebody ask me why I didn't cut a relief angle on the back of a reamer I was making for my revolver. And my answer is basically that it already has a relief angle. When you're cutting in a circular motion, the leading edge is the highest point. So everything behind that leading point is not going to rub because it's already cut the material out of the way. And the only reason for a rake is to keep the cutter from rubbing on the material to begin with. The only reason you would need to add a rake in a cutter like that would be if you were worried if chips were going to get in between the cutter and the material. So yes, you could put a rake on a cutter like that, but if you don't need to, I don't, because I'm trying to keep as much mass as I can on the cutter because of the heat problems. One way to think about it, imagine the cutter as a snow plow. You're pushing the snow out of the way, and your wheels are rolling on the road you just cleared. That being said, I'm no expert. Maybe some tool sharpener who works out there watching this channel might want to pipe in and say, something about it. Anyway, okay, now I'm going to move on to what choice of cutters I use to make the cutter. In this example, you see on the left side, an end mill was used, and on the right side, a dovetail cutter was used. If you'd also notice, each of the cutters cut into the material the same amount of depth. Well, why is this even important? Well, for one, you'll be able to get more teeth on the one on the right than the one on the left. Notice the shape and the mass of the tooth. The one on the right has more material behind the leading edge, making that leading edge much stronger, making it much better for applications like steel, whereas the one on the left would be better for applications like wood. This is generally why I use a dovetail cutter most of the time. Alright, this little bit of information is for cutters that go straight into something like a counterbore type cutter. This type of cutter likes to go all over the place unless it is short and rigid, or it has a pilot on the end of it, with a pilot hole to guide it. So here we have a imaginary rotary table with a 4-jaw chuck attached to it and a piece of bar stock in the end of it. In a counterbore type cutter, the rake needs to be on the front leading edge of the material. So in order to do this, you will come in with an end mill from the front. However, the cutting past center trick doesn't work here, because the rake is on the front cutting edge. If you mill straight into the end of it and go straight back, you're going to make a cut square to the table. The simplest solution I have found is actually just putting a couple shims under the back of your rotary table, and that's enough to tilt it to get your positive rake on your cutting edge. Here I'll show a little bit more detail. The leading edge of the cutter you want on line with center. This type of cutter definitely needs a relief. Why? Because the two flat faces will rub together. Remember our round sideways cutter? Its relief was built in. Here's a photo of a commercially available counterboring tool. Notice how the flutes of the cutter extend into the pilot section. The reason for this is to extend the blade portion past the pilot area. The little groove that's carved into it is for the same reason. The tools that make these tools always will have some sort of a radius on the cutting edge. So when that tool cuts the shoulder for the pilot and where the blade is at, it will leave a small radius. Here is an illustration of this. This little radius left behind by the nose of the cutting tool that made this part would come into contact with the part that you're trying to cut. When this happens, the radius and the corner of the part will rub together and the cutting edge will never make contact with your part. This is where the undercutting and grooving come into play. As you can see in this example, the groove gets rid of that radius and the cutting edge actually goes further and even below the pilot point. Now we come to the chambering reamer. I saved it to last because it has a combination of attributes from some of the other cutters. Although it is technically a horizontal type cutter, because of these little tapers right here, it actually can cut vertically also. Or in other words, it cuts to the side, but because of the tapers, it can plunge into something. To make this, you would set it up very much like the very first cutter I showed in this video, like a slitting saw. Just think of it as a very long slitting saw. The tapers can be thought of as just an extension of the same thing. They're still cutting straight out, but because you put them in a taper, the straight out is at an angle. When you cut the flutes, you don't have to do anything special for the taper portion. You just cut a straight flute. As long as the flute is deep enough to go past the angle, then you're going to have a sharp edge on that angle. So to kind of clarify that a little bit, basically you set it up just like you would with a slitting saw and make just single cuts for your flutes. Imagine you could look at it directly from the top. This is the dovetail cutter cutting into it. The cut you make would have to go the entire length of the cutter. Notice the undercut at the pilot area. This is for the same reason as I explained earlier, so that leading edge of that angle will have a sharp edge all the way to the pilot area. Okay, let's talk about the tapers a little bit. Why does it even have tapers? Especially when the bullet itself doesn't really have tapers around its case or anything. What's the tapers for? My best guess is, and it is a guess, it's just easier. If you were going to have to make an edge like this, you'd have to sharpen that little corner right there, which would make it very difficult. Remember, because of the taper, all you have to do is make one single cut down the length of it. Also, I would believe it'd be helpful in self-centering. And another answer is, if it doesn't hurt and it works well, why not use it? Here's an imaginary bore that we bored out. And we'll overlay it with the shape of the bullet. The first taper actually cut the lands. The second taper, you'll notice there's just a little bit of an air gap where the case meets the bullet. This little air gap will make no difference whatsoever. So again, if it works and it's easy, why not use it? Well, that's probably all the information I can fit into a video like this without making people fall asleep. I hope you liked it. I do want to repeat, though, that I'm not an expert at this. This is just stuff I've learned that has worked for me. So, I mean, there might be other information out there that's better than this. I was just letting you know how I did it. If there's any information that I've left out that you'd like to know, or if you would like me to clarify something more, please comment in the comment section below. I'd appreciate it if you'd like, subscribe, or comment. If you like the content that I've brought you, please consider my Patreon page because the donations help me bring the channel to life. Thanks a lot, guys. Bye.